In this video, I will be explaining a bit about the math behind modeling epidemics. Although I'm using the COVID-19 outbreak as motivation, the SIR model I present is a simplification of the actual events. The purpose is to illustrate mathematically why there are so many possible trajectories for an epidemic and how changing just a single variable, social contacts, can drastically alter the outcome. My name is not Dovid. I am not an epidemiologist, nor am I a medical doctor. My actual name is Dovid, and I'm a math teacher who occasionally dabbles in a bit of science. In order to create a mathematical model of an epidemic, what we're going to do is split the population into compartments. And on the screen you see 5 different compartments. People who are passively immune, that means they got some antibodies from mom. People who are susceptible, exposed, infected, and recovered. And in modeling, we will have movement from one compartment to another, perhaps from exposed to infected. Perhaps they recover and move over there to the R compartment. And just with these 5 compartments, we have quite a few possible models. And it's all based upon the direction of movement. We see, for example, over here that there's movement from the recovered back to the susceptible. That could be because there is not long-lasting immunity. This situation here, we see that people become infected and don't actually recover. So what we're going to want to do for the sake of simplicity, because this is an introductory video, is just use the SIR model. And the SIR model is the classic model. It's the Kermit-McKendrick model. And in it, we are only taking 3 compartments: susceptible, infected, and recovered. We're going to assume a few things. We assume long-lasting immunity, so that way once somebody enters the recovered compartment, they do not move back to susceptible. We also assume a static population, so we're not going to be dealing with births or any natural deaths. Here's the model, and we have our susceptibles, our infecteds, and our recovereds. The sum of these is going to equal our total population. And we have movement, so we have movement across, we have perhaps a bunch more people got infected, we have patient 0 over there in red. He actually had gotten a few people infected while I was doing the first take of this. And more people join, and then perhaps a few move from infected to recovered, and so on. And we see this movement. But instead of dealing with raw numbers, like you see on the screen here, it's going to be a lot easier to deal with fractions. So let's divide everything by n. And when we divide everything by n, we get little s of t plus little I of t plus little r of t, because it's with respect to time, is going to sum up to 1. But we saw movement just a moment ago. And if we have movement, that means we have a derivative. So we have the change of s with respect to time. So we can talk about how is the susceptible fraction changing with respect to time, and there'll be an equation for that shortly. Same thing for the infected. We have that the infected fraction is also changing with respect to time, and again, we'll get an equation for that in just a moment. And finally, we have dr dt. Now, each of these is going to be what is called a differential equation, because it contains a derivative once we write the equation down. Together, they're going to form a system of differential equations. So let's move over to MATLAB now to see what the solutions to a differential equation actually look like, and also what the solutions to a system of differential equations look like. And then we'll return to the SIR model. I get it, not everybody likes math, but still wants to learn a little bit about modeling an epidemic. So go ahead, skip the next 2 minutes, not a big deal. It'll be about 6 minutes of math. So I'm going to introduce differential equations with the logistic model, and this logistic model is slightly different than the classic one you may have seen. This one also has a threshold in it, and this is a differential equation because it contains a derivative. So right over here we see a derivative, dy dt, and what we're looking for is what is y of t, what is it equal to? And that's going to be the solution to the differential equation. And for those of you that have even studied a little bit of calculus know that when you integrate, you get what is called a constant of integration. Therefore, in differential equations, when you solve them, you actually have, due to this constant of integration, infinitely many possible solutions. So we're not going to solve them analytically. Instead, what I'm going to do is show you what those solutions look like. And for this logistic model with the threshold, before I actually graph the solutions, what I'm graphing is called a slope field. And the slope field is going to pretty much tell us where to go. And we imagine that we're starting somewhere along here. We have an initial condition, and I'll put those in a moment. And this slope field tells me where to go. So here it's clear that I'd be moving up. Here it seems to be stabilizing. Over here I'd be descending. And when we add those initial conditions, we have what is called an initial value problem. And an initial value problem is going to be represented on this plane in the time domain with integral curves. Each of these is called an integral curve. So we can just point out a few things about this differential equation, this logistic curve with threshold. One is the sensitivity to the initial condition. It's really important. We look around 4. 4 is this threshold. Anything beneath 4, this population that's being modeled here, does not have enough. It's too low, so it's just going to eventually descend to 0. Above 4, well, actually at 4 it stays. It's the only point. If you stay exactly at 4, we stay at 4 and the population never changes. Slightly above 4, even a tiny, tiny bit, eventually follows this classic logistic curve with this inflection point right here. And it's not that far off from what we're experiencing right now with the COVID-19 epidemic. And we're in this piece of it. And this piece is relatively close to an exponential growth curve. Later, though, it passes through the inflection point and slows down. And it has to, because the population is, of course, limited. This is called, if this is a population model, this would be the sustainability level, or the carrying capacity, rather. This would be the carrying capacity. And above the carrying capacity, we descend down to it. So we have quite a bit of information here in this graph. We see with these little vectors, the direction, or the slope, at any point along any of these integral curves. We also see that we have two very different types of equilibria. This over here would be what is called an unstable equilibrium. Everything moves away from it. This, on the other hand, is a stable equilibrium. But the main thing to take away is the sensitivity to the initial conditions and the various models that we will get as a result. So we just saw a single differential equation and what its solutions look like. Before we could look at some SIR models, we need to introduce a simpler system of differential equations. And what you see on the screen is the predator-prey model. And it is a system of differential equations because we have two differential equations. We have dx dt and we have dy dt that must be solved together, which means that once it's solved, we will be finding some function x of t and some function y of t. So let's look at what the solutions look like now in the plane. And you'll see that there is going to be a slope field as before, but it's actually quite a bit different in that this is not the time axis down here, but instead this represents prey and predator. And it's called a phase plane, and each of these is called a trajectory based upon initial conditions, which is similar to what we talked about before. Instead of having integral curves, we have a trajectory, which means what are the possible routes, so to speak, over the course of time that the prey and predator populations can take. The easiest way to unpack this, I think, is to look at a few of them side by side with their time domain graphs as well. So that was the phase plane, and what I've done is I've selected just 3 of them. And up top, you'll see 3 phase planes. And beneath the corresponding graphs, the solutions, the initial value problems in the time domain. So to interpret that, this is a particular trajectory, this light blue over here. It starts at 2, 2, which means that I've started with 2 prey, 2 predator. And as I unwrap it, as I unpack it, the predator decreases down here, and the prey increases. And you can see that. So as we move around this circle, if we unwrap it, it's not a circle, of course, but if we move around this trajectory, we see how the two are interrelated. So we go down to here, and we would have a point, for example, about 3 and 1.5. So that would represent where the prey is, which would be right around here, and then where the predator is in terms of its population. So unwrapping this trajectory, we can therefore look at the graphs in the time domain, and each of these are the actual solutions. This would be x of t and y of t that we were looking for, the population of prey with respect to time and the population of predator with respect to time, but it's also up here in the phase plane. Now the same thing you'll see for population of 3-3, which means 3 predator, 3 prey, starts here. We unwrap it and we see how they fluctuate, they oscillate, and the same thing over here for 4. One important thing to just note as well, we talked about equilibrium before. This point here is called the center. Is not going to draw any of the trajectories in, but it is still an equilibrium point. So we're about ready to write down the system of differential equations for the SIR model. Before we do, here are some numbers that we're going to need. The first, duration, d, we're going to use in our model, but in fact we use the reciprocal, 1 over d, for gamma. Sigma, the average number of adequate contacts, times tau, the transmissibility, we will write as beta. So beta is going to be sigma times tau. And this can be considered the contact rate. So we're going to use that as well, contact rate. You see the script R there. I've done it in script. I've written it in script so as not to confuse it with the R that we saw already for the recovered compartment. That's the replacement number, and you've probably heard of R naught. It's in the news a lot. R naught is going to equal beta times D. And this number right here, it's really important. Note that it depends on beta, and beta, of course, as I said a moment ago, is sigma times tau times d. And in the model that I present in a few minutes, I'm not going to touch tau or d. The only thing I'm going to play around with is this sigma number here, this sigma, this contact number. Okay, we have enough. We're now ready to write down the system of differential equations. Here they are. The first, ds dt, is going to equal negative beta times I of t, S of t. The next one, di dt, is going to equal beta I of t, S of t, minus gamma I of t. Finally, dr dt is going to equal gamma I of t. Now, of course, you'll notice that this movement out of the susceptible is what's coming in to the infected. This movement out of the infected is what's coming in to the recovered compartments. Altogether, these 3 differential equations form the system. Okay, so we're ready to take a look at the solutions to the SIR model. You see on the screen the system of differential equations. In fact, I've omitted the third because dr dt isn't necessary. If we solve the system that you see, we'll end up with S of t and I of t, and dr dt is just 1 minus the sum of those two. We'll move over to MATLAB now and start by graphing a phase plane. And for this phase plane, what I've done is I've set sigma, the contact number, equal to 3. And I've changed the initial conditions. The initial conditions that I've changed going in are going to be the infected fraction and, as a result, the susceptible fraction. So I'm starting with that there will be 0 in the recovered, which means that the infected fraction plus the susceptible fraction are going to sum to 1, and that's the meaning of this diagonal line right here. So say, for example, right here, I start with an infected fraction, say of 0.1, for example. That means the susceptible fraction would be 0.9. They would add up. So here would be my 0.1, 0.9, somewhere over here. I didn't actually graph that one. This one right here, so we can see it would end up being 0.18 and 0.81, just so you have a sense of where we're starting. Now, depending on where we start, we have different trajectories. These trajectories are going to be the epidemic. And if we start over here down in this bottom right corner, we see that we hit a peak infected fraction right over here, and then it descends down until the infected fraction is 0, and that's the end of the epidemic. It'll be a little bit better for us to analyze this by looking in the time domain. So what we've done in this next display is I've taken 3 phase planes. And as opposed to the previous phase plane that you saw, where I kept sigma constant and changed the initial conditions being the infected fraction and susceptible fraction as well, here I've kept that infected fraction, susceptible fraction the same. I've started with an infected fraction of 1 times 10 to the negative fifth in all of these, and the susceptible fraction being just about 1. It's 1 minus that, so pretty much everyone is susceptible. And I've kept everything else constant. I've kept tau constant, so the transmissibility doesn't change. D constant, I set it to 14, and only changed sigma, and watched what happened as we moved from left to right. And I see that as sigma changes, the trajectories change. They get a lot lower. So I changed sigma from 3 to 2 to 1. In fact, the R0 value also changes. That basic reproduction number also changes. But it's really useful to move from the phase plane to the time domain, and we'll do that right now. So at this point, we start, and this starting point is a very, very low infected number, infected fraction, and pretty much 1 for the susceptible. And as we move, let's follow the red curve, because the red curve represents infected fraction. And right here is the peak of the epidemic, where the highest infected fraction occurs at around 28 days, and then it tapers off down to close to 0. It should be 0. And the susceptibles, on the other hand, decrease, obviously, because they're becoming infected. And at the end, we have something called S infinity. S infinity is going to be the final susceptible fraction, and it's almost 0 here. So in this model, this SIR model, we see that everyone, just about everyone, went from susceptible to infected, and infected then eventually towards recovered. That's not a realistic model for COVID, and the reason for that is that not everyone who gets exposed to the disease is becoming infected. So as a result, a more realistic model would be SEIR, but for the purpose of this introductory video, I've just gone with SIR, and we can still see the effect of lowering the contact number sigma on the trajectory of the epidemic, and still valid in that sense, even though it might not be a perfect fit to the epidemic that's going on right now. Let's look now when we lower sigma. We've lowered sigma from 3 to 2. First of all, the R0 value lowers. We see the trajectory right here. Down here, we see we're starting to flatten the curve, that this peak, it was much higher, it was around 0.6, is significantly lower. It happens later, and it also is a little bit wider, which means that if we're talking about hospitals and how many people, sick people they have to deal with, we're giving them a little bit more time to deal with them, whereas in this first scenario, it was far more concentrated. Let's go a little bit further. Let's lower sigma, the contact number, to 1. Number of adequate contacts is now 1. We see the trajectory dives down here and actually doesn't head towards 0, but actually stops at around 0.10. Yep, that's exactly it, 0.10. And what that looks like in the time domain is quite a bit different. We flattened the curve a lot. We flattened the red curve quite a bit. The infecteds are more spread out. They're happening later as well. But more importantly, not more, but quite important, is that we also, as a result, have the S infinity, the final susceptible fraction, is much higher. So these people are not even contracting the disease. So just by changing sigma, we see how much we can actually affect the course of an epidemic. As I said earlier, I'm a math teacher. I'm not an epidemiologist. So in making this video, I did speak with an epidemiologist, a friend of mine, Michael Levasseur. He's a brilliant professor of epidemiology over at Drexel University. And thank you very much for your help. And any mistakes that are remaining in this video are mine and mine alone.